Thank you all very much for being here. My name is Evan Morikawa, and what are you doing? And by you, I mean you, dear servers. What are you doing? Or our users, what dear users are you doing? Or in my case, what dear API are you doing? I ask this question a lot. I work on building APIs for email, calendar, and contact, which basically means you can do things like curl to get a bunch of email threads out of your mailbox and read it all here as JSON, assuming, of course, we have an internet connection, which was working just earlier. That's unfortunate. That's okay. We can let's kick this one time, and then we'll do it offline mode. Boy, the internet was so good earlier. But anyway, the idea is you would imagine that would return a whole slew of JSON for you from out of your email. We also have the equivalent here to posts to send endpoints. So you can send email wherever you want from any inbox as well. And we're connected. There we go. There we go. Okay. Fantastic. So once again, with internet, you can curl any endpoint and sort of get anything in an email address. You can create, read, update, and delete. And these are the types of APIs that I worry about on a day-to-day basis. And I do this with a company called Nihilus. We're based in San Francisco, have about 35 people total, pretty small, a few years old, and I'm in New York here today. And as a result of sort of in the earlier days of the company of building these APIs, or really just any APIs we're working on locally, it is pretty feasible to just go in and tail a particular log file. It's easier to go in, and just look at the basic logs that you have there with you. But you know, when you are looking at a log file, that's fine for like one request every now and then, but suddenly if you get 10 requests a second, now you sort of see a lot of text scroll past the screen. You know, if you're going at 100 a second, that's a little bit harder. If you're going at 1,000 a second, that's harder still. And sort of now we've gotten to the point where we're dealing with about 1 billion of these a week. So the question becomes, how do you deal with 1 billion requests of data and make sense of any of that, to ask any of these questions I posed earlier? To get a sense of that kind of volume of traffic, I want to try and try and visualize what 1,000 a second feels like. So this here is a bunch of dots that are coming in at about a rate of 10 a second. That's what 10 a second feels like. But if we jack that up to, say, 100 a second, this is about 10 times faster still. Maybe let's look at like 1,000 a second. So when I say something's coming in at 1,000 a second, this is like a feel for the rate at which data is coming in here. Also, like 1 out of maybe 100 or 1,000 like blips red, because maybe that request failed or something like that. 2,000 a second, 10,000, 20,000 a second. So you can see it like starts to it like add up on you very quickly. Another kind of fun way to visualize this is through sound. If you imagine that every request that came in, if you could play a little blip and hear what 10 of those sounds like, what 100 of those sounds like, or what 1,000 of those sounds like, it's like 10 a second. That's like 100 a second. 1,000 a second starts to sound pretty annoying. So that's one way to like visualize volume and flow rate, at least for an API. Although that's not particularly helpful at the end of the day to diagnose exactly what's going on. So as a result, a lot of the rest of this is really talking about some of the more practical diagnostic tools that we use to look at this type of volume of data. And at the end of the day, we're trying to answer questions that are slightly more technical than this, of course, but really, what are these servers doing? Like, what is the API doing? How is it going? Like, are they okay? Are our users happy? Is something like being slow for them? Is it working? And if not, why is it broken? These are pretty fundamental questions to ask. Now, teasing answers out of them at various scales starts to become tricky unless you can start to add in a little bit of data on top of that. So I'm going to start with a little bit of sort of just a basic question, like what is going on? Like what are you doing here? And to answer this, we have, I'm going to show you a little bit of code here to sort of what we specifically do to get into this. We're using Flask, and specifically we're doing it with this WSGI server here is loaded in from gevent. So we're using gevent's WSGI server. And a couple things here. One is that we have overridden the WSGI handler itself, which is significant for a couple things. Is that at the end of every single request, we extend this log request method. At the end of every single request, we log a bunch of information, one per request, and call it like a request handled event. It's kind of like obvious, of course you want to log the event. The one subtlety here that's important is that there is exactly one log per request. But it's tricky because over the span of a request, from getting in data to loading stuff from the database to packaging it up and sending it out again, we might accumulate more and more context along the way. So one thing that we do here is we try very hard to keep like a lot of core pieces of information contained here, but also accumulate data along the way. That gets written to a log file, and it gets sent off to this program here called Honeycomb. Honeycomb is a way to really nicely and quickly, as you'll see, visualize data en masse over time. So for example, here, I'm going to just count the sheer number of queries I have coming in. So that's it over the last 2 hours. Here's it over the last 7 days, the last week. And that is our entire API volume traffic here. You can see this is like peaking at about 2,000 events a second. So visualizing that rate, we come in just shy of 1 billion here over the past 7 days. So great, so we have a general request curve. You can see the weekdays and stuff like that in here. But that's about all you can gain from this information. So the next piece is we need to figure out the right dimensions to start breaking this down. What is useful to split this apart, and how can we visualize that? The first basic one is on every single request, we make sure that we log the endpoint that's being hit. And specifically, we do that now in our Flask code here. This is Flasks before request. It's a pretty common method, but it's a good place to put like everything that should be attached to every single request. Specifically where people are going, the endpoint here. Remember how I said that we only log things once at the very, very end. And the way that we do that is we create this is a Flask environment concept. It's basically just a dictionary that you keep for the duration of your API request. And we start just shoving data into this log context. And as a result, we've sort of built this very nice dictionary full of useful information. And at the very, very end, regardless if it succeeds or not, it's important to also make sure that happens at the end of exceptions and stuff like that. We shove it off into Honeycomb, into all of our other data sources, and as a result, I can now break this down by endpoint. I can also do things like I want to make sure the endpoint exists, does not contain, we have like a delta thing that's not relevant for this. Another good example is like we don't care about our health endpoint because that's not important for looking at this. And then we can run that query once again over the past 7 days. And here's now all of our traffic by endpoint. And by endpoint I mean, so like this is everybody like just getting an individual message, right? This is everybody updating events. And these are all entities that we support that exist on the calendar. So with just that one dimension and the ability to quickly query it here, we can start to already see some slightly more interesting trends that show up here. I noticed that here we've got this like big glob of data on the left here for events API lookup. That's when people like ask us for a calendar event. So it's really useful to be able to go in here and focus just over here, rerun that query for that time span, and take a look at more data here. Okay, well here's like that event. That's a little anomalistic. Let's filter by just that. And once again, we're sort of back at a graph that not quite enough information here yet. One of the other many things we shove into our context is the application, which is basically which user is requesting from our endpoint. So once again, I'll break that down by application ID. And here I actually see something kind of interesting. All of that spike came from one user, from whoever application ID this is. So I'm like, okay, just from like that very quick little bit of diagnosis, now we know that some user is running some big job on like Monday morning. If this becomes a problem, maybe I can reach out and talk to them. But once again, like having the point here is less about this particular case and more just about the more dimensions we can add onto here, the better ways that we can break this down and actually start to answer this question of like, what are people doing? Who's doing it? So that's sort of one way to get at this, like where are people going, what are people doing? Getting the right dimensions and then being able to visualize it quickly is a good start to that. Another question I'd like to ask is sort of, how's it going? And to us, we take that to mean a couple different things. There's basic, like, is it working? But really, it's also a lot about performance. Is it fast? Which is a very important thing when you're building infrastructure that other people need to rely on a lot. And for that, we use response time to look into that. Or at least the one dimension of this I'm going to show right now. And in code, we get the response time all the way at this like whiskey level here. This request time is really just the difference between when the request started and when it ended in seconds. And we send that with every request so we can know by endpoint how well it's doing. So I'm actually going to load that up here. If we bring us back to all of our endpoints again, and let's look at the request time here. So Honeycomb has this cool function called a heat map, which I'll show you in just a second. We're also going to only show like the bottom tail of queries. I know everything is less than half a second anyway, and we load this here. And basically what this is going to show is this will show you a distribution of how fast all of these various requests are over time. And that's for a small section, and we pull this out for the entire week. And it'll recrunch it over the last 7 days, and you can start to see trends about how fast we're doing, like how well things are performing. So you can, this heat map here shows basic things like you can see like densities when traffic comes in for various days and sort of the broad distribution of things. When we talk about request time, it's important to be more specific than just like, yeah, it seems to be fast most of the time. When we talk about average, another way to think about it is this P50 metric, where it's about 50% of the time this particular request is 44 milliseconds. But I don't necessarily care. Experience isn't just about the average experience. It's about the things you remember the worst case scenarios being usually. So we tend to look at the P90 time, which basically means that in this case, 90% of all queries are 116 milliseconds or less. So P90 is a good way, it's a pretty standard metric now to sort of watch any of these numeric metrics to see what's that general experience you're feeling in the worst-ish case scenarios across the board. It's also a good way to identify some of these outliers and pieces that happen here. So this is a pretty fast endpoint, and they're all sort of around here too. Actually, we'll show you one where endpoint contains upload, which is our file upload endpoint here. And you'll see a very different looking distribution here. You'll see that there's a much wider spread in how long this endpoint takes. In this case, this is actually okay, because this is uploading files. So we do expect that, well, people give us files of all manner of different sizes, and this is reflecting, in a way, the distribution of how fast everybody's files, like in our case, those are email attachments, upload to our endpoint here. So this heat map's a pretty cool way to both see, to get an idea of not just your exact P50, P90, or response times, but sort of see how these distributions very quickly and visually spread out over the course of different requests. And as a result, that can get you a pretty good handle as to how it's going for people. Like, is it happening fairly quickly? What is the total end-to-end time that they're experiencing from the entry to the to the system and then out again in the P90 case, or what's the 90th percentile time for people. Another pretty straightforward one is just simply, is it working? This is another very common request that we log as well, but in our case, it is the HTTP status. So if we take a look at that here, across all endpoints, all like significant endpoints again, for the past week, we can see that there's a lot of pretty much 200 requests. Actually, let's take out the endpoints. You can see it across the board. And hopefully, assuming things are going well, we should expect pretty much everything to be 200 okay, some like authorization errors, redirects, and finally some 500s that still unfortunately are happening way down here. But nonetheless, the ratio is the important piece here, is something broken. Now this is not a particularly great way to see, we want our error rate to be very low, like within 0.1% of all API requests. So we have a variety of other ways to watch that, and furthermore alert on it. There's a whole separate talk about observability and monitoring and alerting that I'll refer you to the internet for. But I will say that in our case, in addition, in supplementing the types of quick analysis we can do with a tool like Honeycomb, we also use Sensu to collect a lot of this data. We use PagerDuty to wake us up in the middle of the night if those alerts drop below some level. PagerDuty is pretty common. The way you get alerts to there varies dramatically. We've experimented with Datadog, we've experimented with Sensu. Honeycomb itself can cause alerts, but whatever it is, like you can still set up the query and notify you if anything is going wrong. Because when it comes to the question of is it working, you really want to know as quickly as possible if something is not working. Which leads me to the final question here I'm going to talk about, so if it isn't working one day, the immediate question you always then want to ask is, well, why is it broken? There's a couple ways that we get at this too. One is that, so here I can do an HTTP status, it's greater than 500. So now we're just looking at broken requests here. And furthermore, another important piece of this context that we continue to log as well are the Python exceptions, the error messages. So here we can see there's some like SQL server going away, some sending failure that happened. So logging all those messages as well, in addition to the tracebacks. Flask has the capacity to broadly catch any and every exception. And then we need to make sure that both we like pull all of the sys exe info out properly and make sure we can standardize that to get it back to a useful way to get all the way down to the exact point in our code to diagnose it. Now, another aspect about this type of error watching here is Honeycomb is very good for this sort of broader aggregate thing. Like I can see this has happened a bunch. This is very similar. The equivalent would be Sentry. We also actually use Sentry to keep track of exceptions that get thrown as well. But one thing that is important to note is that at a certain scale, it becomes impractical to store each and every single data point in Honeycomb. So we're actually sampling data here. We're sampling 10 to 1, which means that if I have a specific API request from a specific customer at a specific time, they know that failed, it probably won't be, there's a 90% chance it won't actually be here. So as a result, we not only send all the log data to Honeycomb to keep track of errors, we also use Elastic's like FileBeat service to take all the log data and shove each and every single line into our own Elastic Beanstalk server as well, and then can view that through Elastic's tools like Kibana. But that's sort of this, in a way it kind of is a duplication of data, but they do serve slightly different purposes, which is sort of the point, the main point I'm trying to make here, in that in this world, this is about viewing aggregate data over time. It's about answering like high-level questions very quickly and rapidly. But it is still also important to be able to dive into that one exact log line out of trillions over sort of a significant lifetime of the application being going to help diagnose a problem that happened 2 weeks ago. Another thing is that this is a very fast query system, but only because it keeps a much shorter time frame of data here. And it's set up such that as you get more data, you can say how much you want to keep, and it sort of just falls off the end. So it's good for diagnosis in the now, but there's still a separate system to really answer this question of like, why did a particular thing go wrong at the end of the day somewhere else? And for that, we've been using the Elastic stock for that. Yeah, so between the exceptions and the tracebacks that we send to Honeycomb, between the ones that we get out of Elasticsearch, it gives us a little bit of an answer to why something is broken, which now kind of gives us, to wrap this up, a rough idea of how to answer some of these basic questions that we have. Like, what are our servers doing? What are our users doing? How is the response coming through? Is it working? Why is it broken? And it really kind of comes down to both a little bit of the tools that you have, but also a little bit of a discipline around the particular pieces of data you decide to send, around the dimensions for it, and around the normalizations you put on that data. There are lots of fields that we've experimented with over the times through a lot of trial and error. So there's the exact set of fields that you want don't necessarily come quickly. Once you have them, it makes it a lot easier to very quickly answer these crucial questions, even at 4 o'clock in the morning when something goes horribly wrong. Thank you very much.
Excellent talk. We do have a few minutes for questions, so does anybody have any questions to kick us off? I think in the glasses over there, at the front.
You said you're storing the tracebacks.
Yes.
Are you storing, for example, the request that generated the problem in case you need to debug it?
Yes, so those tracebacks, if any point along the request some exception gets thrown, well, pretty much, depending on the type of exception. Most exceptions are handled in graceful ways, but if it gets all the way up to the top, we will make sure that request actually finishes, actually returns to you a 500 through Flask, as opposed to some Nginx level. Shove the text of the traceback in the log context, and then send it up with everything else. So, which is sort of another theme of this too. You saw we try to push a lot of stuff like into the very first before request block or all the way inside of the WSGI level containers there. So the fewer places there are at the end of the logging that can go wrong, the less chance there is to miss something along the way.
In the red?
You mentioned that you tried the Datadog, that you use Sentry, and there were some other services. Could you give us a comparison? Why
Yeah.
Honeycomb over them?
I would say personally, we're not affiliated with these companies, by the way. Honeycomb has been our most recent favorite. Like you said, being able to do this kind of heat map query immediately and quickly on the fly is an extremely nice thing over, say, Kibana's systems. Kibana has very powerful visualization tools, which is Elastic system. They're a bit cumbersome to set up too. We frankly have not dug deep enough into really setting up a lot of Datadog systems for that as well. We do a lot more server level monitoring, basic CPU usage and stuff like that, and fleet monitoring with Datadog, which is not as great for here. This is about high dimensionality data, breaking it down quickly. And like I said, Kibana and Elastic, we basically use a big the deep archive log stack. You're really going to need to find something. So we have not successfully unified sort of all of these tools because they do serve somewhat semantically different purposes.
I think we'll have 1 or 2 more questions. Yes, in the front row.
So how does Honeycomb store its data?
That's their special thing. We send it to them. We actually just tail log. Specifically, we use the struct log Python library, which basically just shuttles logs as JSON data. Honeytail is a daemon that runs on a box, and it does that. It just tails the log file. It does actually some sampling on the box side, and then it will push everything to their servers. And their whole thing is they store it in a way that lets you do this sort of dimensionality querying by any arbitrary field effectively instantly for some for some recent amount of time. But yeah.
And I think we've got one more. I hope so.
Okay, so if I understand this correctly, so every time you guys get a request, you then pass data to Honeycomb and to Elastic
Yep.
and to Sensu and to PagerDuty as well.
So we currently are just sending it to Honeycomb and Elastic. We also, Sensu can look at, so we also send some stats via StatsD to Graphite as well. So Sensu looks at some of those. There's a lot of different tools in there that can be consolidated. So Honeycomb can actually send alerts directly to PagerDuty. And some of our alerts send it there. So we don't need to, Sensu and PagerDuty do not consume logs at this volume.
Sorry, wonderful. Why they're coming in now, I don't know. Wonderful. Thank you very much for that talk, Evan.
Thank you.